Imagine there's no heaven. It's easy if you try. No hell below us.
Alright, I'm playing. I'm not gonna make you listen to that. There's this artist called Yoko Ono that I found recently. Apparently, she was in part of the group of John Lennon. So, you can look her up yourself if you want to. Alright, so for today's class, I'm not gonna be there. We're gonna be talking about solubility. Okay. When we left off yesterday, I mentioned that not everything is soluble. You saw that firsthand when we did the experiment with last week, as well as before the break, where we did iron sulfide and zinc, or something like that. They're both still an ionic compound, right? The lead iodide that you made is still an ionic compound, but it's not dissolving in water. It's not soluble. It's made a solid. We're going to talk about why. Okay. So this is just a video crash course. I'll link this in the Google post as well. It's a pretty good watch for 11 minutes. Briefly reviews over uh, precipitation reactions and what's happening. But essentially, right, he had two liquids. One silver nitrate, the other one's just regular table salt.
Table salt, good old NaCl.
Right. And when you dissolve it, or sorry, when you mix it, it forms a precipitate. You've seen this before, and that solid is the precipitate that happens. And I believe he gives you the product as well, which he said was silver chloride. Oh, I guess not. Okay, but the product is silver chloride. So, how do we know which things dissolve and which things don't dissolve? Right? Which means things are soluble, which means they do dissolve, or which things are insoluble, which means they don't dissolve. Well, we have these things called solubility rules. There's 11 of them, okay, and they may differ from wherever you go to. You don't need to memorize this, okay. I had to for college. If you're going to go into chemistry, you probably should know this, but you know, you can learn this in college too if you want to, but I'm not expecting you to know this list of rules. But what you do have is on the back of your periodic table, and you have these on the laminated ones as well as the newly printed ones. I'll have the sub pass this out for you. You can have this newly printed ones. They are not laminated yet. I would ask you to please, please, please be careful with them and return it after you're done. Okay, every class should be returning it after you're done. I don't want these to be ruined before I laminate them. I still haven't done it yet. I should. Okay, but I'll teach you how to read this table. There's some things that are soluble, some things that aren't. As you can on the right side, there's this giant solubility rules chart. This is just a visual for me to help you on how to read this chart. There is no need for you to memorize this table either. Okay, this table on the right is solely for me to help you read this chart that you're going to get as a resource. Again, you'll have this on the test as well. Okay. So the rules for solubility really boils down to this table if you really want to condense it and make it so you don't have to memorize these rules. Okay, so how do you read these rules? Okay. So on the top, this is a list of ions that no matter what you have them bound to or have an ionic bond to, they will always be soluble, no matter what. So one of the examples we use is nitrate. If you look on the right, so these are just lists of ions on the X and Y axis. If you look at nitrate and look across, everything is labeled soluble for nitrate. No matter what the partner is, no matter what the cation is for nitrate, everything is always soluble, meaning it will always dissolve in water. No solid will ever form with these two compounds, or something bound with nitrate. So for these ions up top, you have your acetate, you have your ammonium, you have your nitrate, cyanide, hypochlorite, chlorite, chlorate, hyperchlorate. These are all soluble no matter what they're bound to. Okay, I don't think, again, this isn't a complete list, so it doesn't have that example, but nitrate, you can see, that's what it'll look like. Everything that you can think of, any metal that you can think of, any cation, no matter what, it will always be soluble. Okay. Bromine has some exceptions though. Bromine, chlorine, iodine, and sulfate. They all have some exceptions, and that's what is listed up on the right. So bromine is soluble for everything, no matter what they're bound to, except for these three elements: silver, lead, or mercury. So if you look at bromine, it doesn't have everything on here, but if you look to the right, in the first few columns, everything is soluble until it gets to silver, one of the exceptions. And then lead. Now, it says slightly soluble. We're not going to worry about slightly soluble. We're going to go for all or nothing, like completely soluble or not soluble. This will be more topic we'll talk about later that we're not going to cover. What's missing is mercury on here, but you can see that mercury, it will probably be an insoluble as well. Okay. This is true for iodine, right? Insoluble under silver, insoluble under lead and mercury, but everything else is soluble. Sulfate, okay, has different rules. Sr for strontium, Ba for barium. It has barium here, so insoluble. Has lead, Pb again, insoluble. Right, you go from sulfate to lead, insoluble, and then mercury, obviously not in here. I know there's other 2 ones. Again, we're not going to really worry about the slightly soluble ones. Right, chemistry is finicky. There are a bunch of rules, and it doesn't always fit neatly in a package. But if you follow the rules on this page, that's all you're expected to know. You don't need to know anything else besides that. So that covers the top part, where it's saying that every single one of these is always soluble, except for a few cations they're going to be bonded to. On the bottom, it's opposite. They are always insoluble except for the few compounds or for cations it's bound to. So carbonate, right, CO3, phosphate, PO4, chromate, dichromate. Any compound with these anions in there will always be insoluble, with the exception of if these anions are bound to an AH4, which is ammonium ion, or an alkali metal cation. Remember, an alkali metal is a group 1 metal. That is the lithiums, that is the sodiums, that is the potassiums. Yes, it goes more, but the table doesn't have any. So we can look at the example, right? Carbonate, it has carbonate up here. Everything is soluble in group 1 and ammonium, but everything else is insoluble. Right? Besides the group 1 cations and the ammonium cation, everything else is insoluble. That's what the bottom table is saying. Okay. So these are the exceptions where they makes it soluble, which is the opposite of the exceptions on the top half of the chart. You have your hydroxide. If you look on right here on the right, the hydroxide, everything is insoluble except for ammonium again, and alkali metals, and a few other like calcium and barium and strontium. Again, slightly soluble. Again, don't worry about it. Follow the chart. So hopefully this kind of helps you to figure out which ionic compounds are soluble or insoluble. Now, what does this mean in terms of inside a chemical reaction? Like, how do you visualize like what's going on? What does having being insoluble and not soluble like have to do with forming a precipitate inside a reaction? So in this video, it shows a quick demonstration of what's happening on the molecular level. Remember, when you have water, all these gray areas are the water molecules, and you put an ionic compound in there. The ion dipole interaction between the water and the molecules and the ionic ionic atoms of the ionic compound, right? It's going to pull them apart and then surround them so that they can't reconnect, and they're just going to be floating about in the water. Now, this simulation is going to remove the water to help you see clear, but he has a barrier where he has two different substances dissolve, right? Sodium chloride and silver nitrate. That's what we was shown in the earlier video as well. So on the left is just sodium chloride. On the right is silver nitrate. As you can see, you have just sodium and chloride ions, whereas here you have silver and nitrate ions, right? Nitrate is NO3, so you have N and 3 O's. Okay. So with this barrier, right now they're separated. They can't interact with each other. Right? They're both soluble. If you look on a solubility chart for silver nitrate, right? So if you use this chart, silver nitrate, it is a nitrate compound. Every nitrate is always soluble. So it's going to be dissolved in solution. The water molecule is able to pull it apart. The other compound was sodium chloride. Chloride are all soluble except for these four. These three. Sodium is not one of these three. So chloride compounds are all soluble as well. So sodium chloride, table salt, soluble. So is silver nitrate. And what happens is that if you remove this barrier where you allow these four entities to start intermingling, right? Remember, it's just a random flow because it's water. Things are going to flow about, so they're going to float about. And whenever a silver and a chloride ion meet, they're going to smack and stick together because a silver and a chloride ion will make an insoluble product or make an insoluble compound. What that means is anytime these two meet, they'll, for a split second, bond together, and as soon as that bond happens, it will fall out of solution, meaning it will no longer be surrounded by water. It will be attached to other chloride and silver ions and start making the lattice structure again. So that's what this image is showing. Once it meets more of the silvers and the chlorides, it's going to start reforming the lattice structure. So imagine there's millions of each of these particles. They're going to start attaching to each other and then start forming the lattice structure, which is the solid. That is essentially on the molecular level how a precipitate forms. So and I want to capture that last image. All right, if you zoomed out, so these chunks, they each individual form small chunks, and then once they meet, they'll make bigger chunks. So it's kind of like, I don't know, I'm sure you play video games where you like, you guys play Slidaria or whatever. You got all these worms growing bigger, and then when you eat that worm, you absorb all of it and get really big and stuff like that. So eventually, it'll look like a white powder that's forming in the liquid, because remember that silver chloride cannot dissolve. Okay. So what are you going to do with this information? Well, I have a worksheet for you that your sub will pass out or should have passed out. It's this. It's really simple. It's one page. Okay. This is going to be due on Thursday night. So you have Wednesday and you have Thursday to do it. So it'll be due Thursday night. But got some singing in the background, so don't worry about that. Also, I'm doing hand gestures, so I don't know. There's no video. Anyway, it's really simple. You look at these compounds from A to P. It's going to list the compound, the ionic compound, and then it could give you the name or the core formula. But either way, you need to tell me if it's soluble or insoluble. So, for example, potassium bromide. Look on the table, on the chart. You look at potassium, you look at bromide. You usually look at the anion because you want to look at the anion first. So you look at bromide. Is K one of these exceptions? No. So that means potassium bromide is indeed soluble, right? So you put soluble, move on to the next problem, so on and so forth. That's what you do for A through P. Next is the K, this bottom part, number 2. This is a little bit different. I give you 2 different ionic compounds. Your task is to make 2 new compounds that would potentially react and form new compounds if they reacted, right? So if you have KBr reacting with AgNO3, your new product would be KNO3, right? It's a double replacement reaction, so you switch partners, KNO3, and AgBr. Right? Ag becomes with the Br, K becomes an NO3. Remember, the metal or the cation is always listed first, followed by the anion. Okay? So the anion should always be second. After you have done that, you need to underline the compound that would precipitate from the solution. Or in other words, it would form a solid, or it's insoluble, right? Precipitates are compounds that are insoluble. So underline it. I know you can't see it, but this is underlined. This is what you'll do for all the rest of the boxes. You form your two new compounds from a double replacement reaction, and then underline the one, or circle, I guess. You don't need to worry about spectator ions. We'll talk about more about this in a little bit. But if you want to, just real quick, spectator ions are ions that don't end up forming anything. Right? They're going to be still dissolved in solution. So this KNO3 will be a spectator ion, meaning it's just watching. Right? It's still going to be dissolved in water because it's soluble. It's just going to be floating about. They're going to be dissolved. The ions aren't connected. So it's just going to be watching AgBr kind of falling out and leaving it. So that's what spectator is. If you don't understand it, it's fine. Ignore it. We'll cover it more when I come back. But for now, you need to at least underline AgBr, okay, or whatever one is insoluble. This worksheet is on Google online. I will also post the answer key. So like you can cheat, but think about if that's gonna actually help you. Okay. If you have any questions, send me a remind. I may or may not answer. I may be busy. We'll see. But that's the assignment for today. Okay. All right. Peace.